apresentação. Bom, novamente, boa tarde a todos. Em nome da Escola de Engenharia, em particular dos programas de pós-graduação, eu dou as boas-vindas a todos, né? Esse é o nosso segundo seminário do ciclo de seminários do segundo semestre de 2021, né? Comemorando aí os 125 anos da Escola de Engenharia, né, com um foco bem grande em internacionalização. Então, a gente tem o prazer hoje de receber o nosso segundo palestrante, o professor Ludwig Cardon, da Ghent University. Tá? Ele, obviamente, o seminário vai ser ministrado em inglês, tá? E eu vou passar a palavra para o professor Guilhermino, que vai conduzir os trabalhos. Mas antes disso, eu queria fazer mais uma observação em português para os alunos de graduação, né, da mesma forma como a gente vem fazendo nesse ciclo de seminários, vocês vão ter três checkpoints para ganhar horas complementares. Vocês precisam responder a pelo menos 2 desses para ganhar horas complementares, tá certo? Perguntas, se vocês tiverem, por favor, façam no ícone Q&A, né? Q&A. Pode fazer em português, o professor Guilhermino vai fazer depois as perguntas, né, para o palestrante. Tá? Então, vou passar para o inglês agora e falar algumas coisas e passar a palavra para o professor Guilhermino. So, again, welcome everyone. To the second seminar in the cycle of seminars of the postgraduate programs of the School of Engineering, celebrating the 125 years of our School of Engineering. It's a pleasure to receive here Professor Ludwig Cardon, even if it's receiving him virtually in our university. Professor Cardon is from Ghent University, and he's a specialist in polymers. So the chair of the session will be Professor Guilhermino. So I'll pass the words to him. If questions, you can make in the Q&A icon here, and Guilhermino will read to the speaker after he finishes. Again, welcome everyone. Welcome in particular Professor Ludwig Cardon, and I pass on to Guilhermino.
Okay, good afternoon everyone. So first of all, I'd like to thank Professor Ludwig Cardon to accept our invitation, and for me it's an honor to have you here, Professor Ludwig. We start to talk in the beginning of this year, so maybe in few months I will be able to visit you, and maybe you can come to Brazil and know Mackenzie University, our campus, our labs, and everything. So let me introduce Professor Ludwig very shortly. Professor Ludwig Cardon is Associate Professor at Ghent University, Belgium. He holds a PhD issued by Birmingham City University, UK. His research field is in characterization and processing of polymer and composites. He has published several papers in the most important polymer and material science journals. He is associate editor of Plastics, Rubbers, and the Composite Macromolecular Engineering, and top editor of Materials DPI, Material and Process Innovation for 3D Printing Application. So, dear Professor, you have no limit of time, of course, no more than 1 hour maybe. I know that it's quite late for you in Belgium. It's 5 hours ahead. So, but be free to present your seminar. Thank you so much.
Okay, thank you, Professor Guilhermino, to first of all invite, and I especially thank also in name of our rector this invitation, and especially also congratulate you with, let's say, the 125 years of the Mackenzie University. We also noticed that this celebration is very important We had our celebration in 2017, which a little bit older than yours, that we celebrate 200 years of university. So the strange thing we always say in that manner is that we are even older than the official life, let's say, of our country, Belgium. So as we were part, let's say, in the past, the Flanders, the Flemish part, the Dutch part of Belgium was a part of what we call the low lands, so the Netherlands, in the past, so more than 150 years ago. Then, so it's a great pleasure to present the research we do in our group. So I will try to share my screen first. Okay, you can see my screen?
Yes.
Okay, so yeah, what I will try to do in the upcoming briefly 1 hour is to give a brief presentation. One side, what's Ghent University, what's our laboratory, our department, and then going more in detail about with what I call some case studies. I selected something like 10 case studies to explain how we try to innovate in, let's say, in one side, the polymer processing itself, but on the other sides, also the material science, the polymer and composite material science behind that. So yeah, I select a title like Sustainable 3D Processing and Characterization of Polymers and Composites in general approach. So why I mention general mention it as sustainable, because it becomes more and more important. You also know, expect all of you, the United Nations has its goals in sustainability. So, and that's also something we pay attention for in our, let's say, in our university, and also within our department and research group. I mean, for instance, you will see in the case studies the aspects of recycling, circular approach of using materials and processes. So why 3D processing? Okay, it's processing in general, but 3D, why we spend a lot of attention also on the processing of composites and polymers by additive manufacturing technologies, which are, people talk about like 3D printing. So that is general introduction. So briefly presenting our team. We, with our research group, we are part of the Faculty of Engineering and Architecture. And within our Faculty of Architecture and Engineering, we have several departments, and we belong to the Department of Materials, Textiles, and Chemical Technology. And chemical engineering. For the moment, our group has 2 professors. So besides me, we have also my colleague, Flavio Marchesini. He is associate professor since this year, since 1st of September. So he's really what I would call a new professor. And the nice thing to mention, you can see it also in the small summary, he was also a senior researcher at Halliburton in Brazil. So he's from origin from Brazil, but yeah, he is also Italian. So that's in that manner. I know a lot of people in Portugal, also some people in Brazil. So Marchesini, it's an Italian name, I would say, in Belgium, but it's not like a Portuguese like. So he's officially a Brazilian. So that's briefly to give the overview of our professors in the group. In total, yeah, briefly mention that for my part, but in total we have almost 30 people in our group with yeah, some administrative and technical staff, but mainly all our staff, briefly 20 of them are PhD students, and then we have 3 postdoc researchers. To give a small insights, in Ghent and Ghent University, because yeah, we are on the other side of the ocean, we can say. So it's far away. By plane, I still remember it's something like 8 hours, I thought, traveling. So you have here a nice view, helicopter view, I would say, from the city center of Ghent. And we use that picture a lot of times because, yeah, I will change my pointer. Let's make it more a little bit easy. I hope you see the laser type pointer now. So this big tower you see is the university library. It's completely renovated since recently. Then the building you see on the backside here, that's the originally, let's say, first building from the university, in which one also the Faculty of Science and the Faculty of Engineering was established. Nowadays, it's our, let's say, Dean's office, but mainly our laboratories are outside city center because the labs became too small. So that's our rectorate on the left side. And then on the back side in the middle, on the horizon, let's say, you see the university hospital. So we are a kind of comprehensive university with several disciplines, and also including a university hospital which serves education, but also do a lot of research, like in cancer, health for children, and so on and so on. So to have a nice walk, very brief walk, I don't show a video, otherwise it will take too much time. But let's say this is Ghent by night or Ghent by day, the other pictures, with historical buildings from the medieval period. And then also, like you can see here, some modern architecture also integrated. So Ghent is a medieval city. Sometimes we call it medieval. But also we want to say it's a student city. And you can see that on the number of inhabitants. So we have around 250,000 people. But yeah, when it's student time, then we have almost 80,000 students. So a lot of them living in Ghent are student houses, so students a lot. And a lot of nationalities. Yeah, and as you can expect, a lot of restaurants, but also a lot of startups. So these people who want to start up themselves from experience, let's say from study at university, starting up an own company, a one-man or two-man company like that. Some other nice pictures. So we have yeah, also very old paints, some nice view. We have a castle of the Counts of Ghent from the medieval period. Some nice vegetables, and also Ghent is what we call a bike-ly friendly city. So driving by car is, let's say, not always easy. You have to pay attention for the bicycles. So yeah, I show you already this campus in the first photograph. So this is the map of all our campuses. We have campus inside city center and outside city center. So, and this is, let's say, the rectorate and the main campus of the university, but we are just outside city center. So this is what we call our Ghent Tech Lane Science Park. And to briefly annotate, so this building here, it's our polymer processing building, in which one we have our processing equipment and characterization. But besides that, the buildings you see here, which I indicated by laser pointer, these buildings are also related to our department, which are what we call then the chemical engineering and also the polymer chemistry engineering. So that briefly about Ghent and Ghent University. So activities in our research group, we focus on labs and semi-industrial scale polymer processing and polymer engineering. This is very difficult, very different disciplines. So I mean, it's extrusion, special extrusion applications, injection molding, additive manufacturing, focusing on the polymer additive manufacturing or 3D printing. Experimental design and process simulations, flow simulations we are applying. And we also have in our lab, the integrated Fab Lab. Fab Lab, it's a kind of maker place for our students and researchers. So we have the single and multiple multi-phase analysis and control of flow of materials. So we do the experimental and rheokinetics and quantitative modeling of polymers and rheology. So and we also have polymer characterization and design. What do we mean with that? So we have the standard characterization after processing, but we also do the design of polymers, so the blending and additivation and so on to develop new materials. But especially also important, I mentioned sustainability in my title. So polymer circularity and recycling is very important in our research group. So very small insight in equipment, injection molding, extrusion compounding, blow molding and thermoforming, very briefly. All molds like you see them for extrusion, blow molding, injection molding, all these type of molds we always develop in-house, and we integrate in these kind of molds also, let's say, special features which occur also in industrial applications, and to try to mimic problems that can occur later on. So an insight of the big production, what we call the semi-industrial facilities. So we have a co-extrusion line. On the back side, you see the plate extrusion up to 1, 3, or 5 layers. And then in front, we can also use the so-called 1, 2, or 3 foil blow principle for foil extrusion. Besides that, we cooperate together with our colleagues of the textile research group in our department, which is my colleague, Professor Dogo, responsible. And we do the co-extrusion of filaments for textiles, so yarn for artificial turf as example. So, and then the third main part is the additive manufacturing, which we have at one side the extrusion-based technologies, the sintering technologies, and also have the possibility to develop our own filaments and blends. So some other experimental facilities is reactive extrusion. This one is not yet arrived. It will arrive very soon, within 2 months. It's new equipment which want to investigate reactive extrusion, blending and designing of new type of polymers and composites. So, and then the mechanical and thermal analysis and rheological analysis as brief example of equipment. We don't have all equipment you need in polymer engineering. We also use equipment from other labs, other groups, depending on the needs. So that briefly the overview of the university and the labs. So I will dive somewhat more in detail, and I think it's a lot more interesting for you to know in some case studies. What I will try to do is, for each case study, I briefly explain how we tackle the research and what we try to improve or investigate with these kind of topics. So the first one I want to discuss briefly. A first case study we investigate is a so-called stabilization of ABS materials. So it's so that when you buy ABS as a virgin material, a lot of times these type of materials have already been stabilized, especially, let's say, in scope of oxidation. But we noticed ourselves that when you use them one time, that the original pellets are not always as after one processing. So what we did in this investigation, we combined spectroscopic analysis and FTR, thermal analysis technologies, and color. So we identified the yellowing during or after processing. So we start, as you can see on the top of the slide, with at one side the ABS made by emulsion polymerization and the other one by mass polymerization. So we selected the two types of ABS polymer processing. So what we did a modeling predicting what we normally could expect as due to the type of blend. We are applying also the effect on the aging, on the antioxidation, let's say, or the oxidation. So we work at one side, you can see here the virgin materials. We also did experimental blending with two types of antioxidants. And then we find out how the reaction of the material was interfering depending on the processing parameters. So this is a kind of one of the examples of material improvement we want to achieve. For instance, this investigation was a pre-study to understand when you would use ABS materials in a circular economy. Once you buy virgin materials and you have to use them and you want to reprocess let's say post-consumer or post-industrial polymers, when you want to reuse them, what would be the expected effect on the oxidation or the aging? So also we try to find out, and I don't present all of it because of lack of time, but what we also investigate is, let's say in this scope also, the effect of the processing temperature. Processing temperature, or for instance also shear effects which are induced inside the design or the extruder you apply. So that is a first example of research we are doing. So a second part I briefly want to introduce, it's what we call hybrid molds. It was one of my first research I did years ago, I thought around 30 years ago, during my PhD study. What do we call hybrid molds? Well, I try easily to explain you. So in general, when you design for polymer processing, can be either injection molding or thermoforming, let's say. When you design a mold, and then you have, let's say here your injection unit, the mold itself is mainly produced in steel. But we know all that steel, it's very good for a heat transfer. But once you want to produce short production runs, an option, a possibility is to replace the inserts, the core cavity you use inside your mold, to replace them by other type of materials. So some of them, I will show you immediately some results on that. Some of them that we applied was, for instance, an aluminum mold, let's say a titanium mold insert, or even 3D printed plastic molds. So we develop plastic inserts, we incorporate them here. So one is our mold flame, two is our cooling system, and three is, let's say in this case, our 3D printed polyamide 11 mold. So people would say polyamide we can't use for a mold. Well, you see this setup design on the bottom. You see here the molds near, let's say, the machine. So what we then do, we inject, in this case with a screw gate, we have our part. It's a kind of play tool we produced, but we investigate in between steel and in between the polyamide insert, what's the cooling behavior and what's the behavior of the material you inject inside that mold. So what we do, we use software like Moldex flow simulation. We investigate the thermal behavior of the steel, of the polyamide polymer insert in which one we inject polymer, and we look for an inside a closed cooling system. So we close the mold, we look inside a closed cooling for 7 seconds for a steel, the same for a plastic mold insert, and then 18 seconds also. So as you can see briefly on the figure, this steel mold cools down very fast. This one is not yet cold. The part also is not yet solidified. This one is better, so we need a very long cooling time. So yeah, you see also some varying of the insert itself. So why is this important? Well, with this kind of hybrid molds, the temperature shear stress during the filling, you fully can investigate by modeling, but you also can analyze that by experimental investigation. So that's what we try to investigate, and we also try to reduce in that manner the injection pressure. Because when you have a mold like plastics, you inject plastic in plastic, the plastic will not solidify. So this means the injection pressure you need is a lot lower. So it's that what we try to investigate, and which also has the effect then on your shear stress and lower injection pressures you can apply. So, okay, I will pass by these slides, but this one I show you already in the overview, but more important for you to explain will be this one. So when you have the P20 steel, standard steel mold, you can identify inside the flow simulation, you can identify the so-called skin layer. What does this mean? The top and bottom of your mold, you cool down. When it's in steel, this one will cool down very fast and becomes, let's say, blue. But the inside, you have the contact with the mold, which creates your skin layer, and the inside will cool down somewhat slower. So when you inject polypropylene material, the crystallinity in the middle will be higher compared with your skin layer, which is more amorphous structure. So when we then inject inside a plastic mold, Then we notice the green one means it's not yet fully cooled down. So what we notice that the temperature of your skin layer is a lot higher. So the crystallinity of your whole morphology of your polymer you inject is finally completely different. So that's what we investigate, for instance, and you see that here on the bottom, on the left side, it's a standard skin layer you see in a steel mold when you inject the polymer, and here you have a little bit your spheroid structure with semi-crystalline polyprop material. But then you see in this one, you almost have no skin layer in contact with the cold, after a while cold plastic mold, but inside you see a lot of spheroids which are initiated due to the very slow cooling down. What's now important in that one, we are further investigating this topic the next months. Well, this is very important because the difference in crystallinity in morphology will finally result in a difference in, for instance, impact behavior in brittleness of your material. So also what we investigate in that case is, let's say, the surface structure. I briefly showed that here as an example. We do process optimization to define what's the minimum needed holding pressure. And we look inside the surface quality by, for instance, in this case, we do it by contactless, Kayens contactless surface roughness measurement. So you see with the EDM steel roughness, the vapor fusing of a polyamide 3D printed insert, but with a special surface treatment. They also can treat the surface by bead blasted or dye principle. So, and you see the difference in the scope of the roughness. So this is also some investigation in combination with the morphology and flow behavior and cooling principle. So what we analyze in that one too is, let's say, to optimize finally the cooling times, because you want to cool down as fast as possible. I'm not sure, I think I didn't integrate a slide on that one, but what we then design also is the so-called forced cooling. So what we do, once the part is cooled down enough to be solid, we open the mold, we eject the part, and then this mold insert, we cool down that one by forced pressurized cold air stream. So to be able, what you see on the left side, to be able to, instead of standard air, to have a forced cooling, so a faster cooling and a shorter cycle time. So this is an example how we investigate that. For those who like that, I mentioned also in the presentation the reference of the recently published paper on this research. Okay, that was somewhat trying briefly explain the interrelation, let's say, to the polymer processing, mold design, and material behavior we investigate. So a third case, a study case I want to present, it's the design of fused filament fabrication technologies. This is for us also standard polymer processing, I would say. So everybody knows 3D printing, in which one, I hope you know, let's say, in which one you have a gear wheel that push a filament through a heated nozzle, and then they deposit layer by layer. So what we do in our research, we divide this kind of printer systems, extrusion-based micro extrusion systems, we divide them in 4 zones. So zone number 1 is what we call our feeding, where the filament is still in solid phase. Zone number 2 is the heat sink in between the free filament and the guidance. This one is cooled down. And then we have zone 3 and 4, which is the nozzle itself, and finally the deposition of the substrate and the cooling down. So you somewhat can see here that we cool down, so the hot becomes yellow, from red to yellow, to indicate the cooling down process of the system. So what we try to investigate also in this case, from experience from standard extrusion, is to investigate, as you can see, the distance from the exit. So this means when we would have a free flow material underneath the nozzle, not on a substrate itself. So when we extrude the material, what happens with your material in the scope of die swell due to, let's say, a kind of latent internal pressure? in the material. So depending on the distance and depending on the different type of models, the PTT or cross model or Newtonian model, we try to mimic the die swell that happens in this kind of micro devices. So you can understand immediately, to be able to investigate this one, that you need the rheological curves of these kind of materials, of the polymer you want to process. You have to understand the design of the very small nozzles, let's say in this case 0.3 millimeter. So, and then we define the distance from the exit. So from this position up to downwards, we define the distance and we find out what's the die swell from the material itself as a die swell ratio. So combined with that one, we also look inside the material for the maximum stress. And you see as example here in this case, we also look inside depending on the flow behavior, depending on the deposition rate and the cooling system and the die swell. We want to investigate what we call the intra and interlayer adhesion of the filaments of the substrate you deposit. So, and then we try to play, let's say, instead of big gaps, yeah, you think it's a very big gap, but finally it's a small amount. It's some image, stereoelectron microscope image. So this very small voids, we try to reduce them by optimizing, let's say, the shear effect by reducing the die swell and so on. So there is a lot of combination of flow behavior and material science for the so-called welding of the strands. So that briefly tried to illustrate how we combine again material science and machine development and engineering. So a fourth case I briefly want to illustrate is the so-called design for advanced composite 3D printing. So briefly explaining, so in general, normally 3D printing is what you'll see here on top. And then we call that as final result, the so-called stair stepping. So stair stepping, what does this mean? You build in 3D printing layer by layer, but this means you print, let's say, one material and another material. So you have a kind of steps and there is not a perfect mimicking of the outer surface. So what we developed ourselves is, let's say the inner printing is like that. And then we do a 5-axis printing on, we call it curved layer additive manufacturing, in which one we follow the path and we try to optimize the surface roughness or structure of the printing. Besides that, we also combine that with fibers itself. So we developed pultrusion system. So you pull your glass or carbon fiber through the nozzle, and then the polymer will flow around the material. So we do the wetting, we do the infiltration of the polymer inside the fiber. A second method we developed is a passive spreader pin. A third method is what we call the active pin. What does this mean? The fiber will flow around this one, and the material will be pushed. So we spread out the fibers, but the material will be pushed in between the fibers. The method of the active pin is we have the filaments of the fiber flowing around the wheel, around the pin, and from internal, we inject the polymer, the matrix material inside the fiber filaments. So to improve the infiltration. So this is the result you can see here. So we have fibers from the pultrusion, which are not wetted, so it's not infiltrated. This is the passive pin, and this is finally the optimal one, the active pin method for impregnation of fibers, either glass or carbon fiber. So after printing, you print several layers, and the triangle, what you see, it's small voids, which we still have to improve in the process. This gives you a microscope image about the distribution of, let's say, the fibers in layer 1 and the fibers in layer 2. So you can see there is a good distribution. When we compare that, I don't have an image immediately on my slides, but when you compare that, for instance, with the Markforged fiber 3D printing, the amount of fiber is a lot less, and also the fiber distribution is really low. So that we also investigate by finding out the distribution of the fibers, which I briefly show here from the pultrusion, the passive pin, and the good distribution of the active pin, spreader pin. So also impregnation is important. So we calculate the angles, the impregnation possibilities for spreading out the fibers. And we also investigate the flow of the material, because a normal 3D printing filament has a certain flow and they spread out a certain section. So in our system, the fibers will pass through the infiltration system, but then we have to pay attention on the speed of deposition compared with the filaments, the fibers which are passing by here. So the fibers, when they are glass or carbon fibers, they are, let's say, not flexible, which you have in a standard 3D printing of your polymer. You have the viscoelastic behavior. So in the scope of the fibers, we must pay attention that the speed inside this one, it's compared completely equal to the deposition rate you apply. So that's also what we try to investigate. A fifth case, it's investigation of the rheology versus thermal degradation of polymers. I briefly showed that, how we do that in that case. So it's the work of my colleague Flavio Marchesini, together with the researchers of our group. So what we investigate in that one, we use in this case on a commercial polystyrene reference material. So we use plate-plate uriometry. We use TGA also to define the ideal rheological temperature we want to apply. So, and then we look inside the rheology versus molecular weight and the rheology versus a given degradation time. Why is this finally important? Well, when we investigate this one, as you can see, the G prime, G double prime for virgin and for aged materials, this is very important for us in the scope of either standard extrusion processing or, let's say, the extrusion-based 3D printing. To know, let's say, the lifetime or the residence time of your polymer inside your extruder, and to try to redesign extruders so that the residence time is not too high or the shear effect inside your extruder is not too high, and to avoid degradation during your polymer processing. So another aspect in the flow behavior we investigate is a so-called die swell. So I mentioned that very briefly before in the scope of 3D printing, but in this case, we investigate that one also in the scope of a standard extruder. What we did, and I think it's in the next slide very briefly, I pass by somewhat faster. What we do, we developed a system with two cameras. These cameras are high-speed cameras in which one we combine with, let's say, with video capturing. So we capture the processing itself of the polymer. We measure the variation when it would occur, the variation of the die swell. And by mimicking that one, going back to the previous slide, by mimicking that one, we look inside the output pressure. We try to have a uniform flow. When there is a variation, we can control the speed or the flow behavior, the stability of the extruder. But on the other hand, what's also illustrated here, taking in mind the aging, we also look inside the molecular variations, the shear effects, and finally trying to find out what happens with the different steps of your polymer. So what I mean for that, so depending on the molecular variations inside your material, and the type of blend could be a polypropylene, let's say, with a small, with a low or a high molecular mass. Depending on that one, we have a different die swell. So that's what we also try to investigate, how there is the effect of the compression, the shear effects inside materials. So this was investigated using, let's say, constitutive models by using the standard Cross-Sloban Maxwell and also the PTT model. What we find out, I go somewhat to the next slide on that one to showcase, what we find out that mimicking the whole process was rather optimal, taking in mind the so-called PTT model, in which one you try to mimic the effect of the die swell based on polypropylene. Okay, so you can read that all the details also, for instance, in the Journal of Physics of Fluids, in which one we compared between the 3D and 2D models, which we developed, and to find out finally if it's possible to predict it on a 3D level, which is important not only for the flow behavior, but it's also, or the visualization, it's also very important in the scope of the behavior of your polymer inside finally the extruded part. So you see some ideas here in this case of what finally happens depending on our center line, depending on the width of the die, and so on, the effect of the die swell itself. So I pass by a little bit faster to avoid lack of time for discussing also other topics. So you see here also, and briefly explained, you have the velocity profile of a material. When you push it through your extruder and your die, the inside velocity is high. At the wall itself, we have a velocity 0. Due to that effect, you create finally your die swell. So due to the pressure, induced pressure. And then finally, at the end, when you don't have any more the die swell, or when the die swell pressure was occurred, we have a uniform, straightforward flow of velocity of our material. So, and that's also the correlation, briefly to mention on that, that's also the correlation we do in, let's say, die design. Inside an, for instance, a co-extrusion die, they try to mimic a uniform flow inside the die, and they try to avoid you have a higher flow when you exit, a higher flow in the middle of the die and the lower at the borders. So this is also a reverse you can do. Based on this information, you can redesign the internal structure of a die, finally that this pressure or speed distribution is equal when the polymer would exit finally the die, and you don't initiate then a die swell. So that briefly as how we interact with technologies. So that's very briefly on die design and rheology investigation. Another case study very briefly, what we do is microfibrillaire composites. This is also, let's say, an important part in the scope of recycling of materials. What I mean for that, in recycling, for instance, yeah, we call that here in Belgium the blue bag. You put all your plastic waste of PET bottles with PP or HDPE caps on top. You put them in the bag, they recycle, they collect that separately. So, and finally, in this case, you see material A and B. B is the inside material, which is, for instance, PET material, let's say 20% of PET material. So the red one, material A, it's a polypropylene. When you would have a 20-80 average mixture of that one, let's say in waste, and then what we do in this case, we take the material, first we do thorough blending, but after the blending, we do so the so-called cold stretching. So by cold stretching, we create fibrillization. So we will have small fibrils of the PET material instead of spherical. And we have surrounded polypropylene material. So we cut that in small pieces, and then we inject at a lower temperature so that finally our polypropylene will melt, but our PET material will not melt. So by using the right processing parameters and blending strategy, you can create the so-called microfibrillaire composites. You can expect immediately that polypropylene and PET materials do not adhere well. So you have no good adhesion, but you see here the fibrils. And when we can initiate a better adhesion in between the PET and the polypropylene material, you can create finally a more impact resistant composite, microfibrillaire composite. That is one example. Another possibility would be that when you can use, let's say, two types of polypropylenes with different molecular mass or melting behavior, you can use a one type material with perhaps a microfibrillaire structure inside. So this is further research we want to do in future. I know that Professor Guillermino Fecin, you like also fillers. So I integrated also one of our research in the scope of developing of strain sensors. So strain sensors can be applied in several applications. So you see here some possibilities. So it can be a wearable human-machine interface. It can be like, let's say, soft robotics. digital tactile systems, 3D printed strain sensors, and so on. And they have a lot of applications, like, let's say, in robotics, biomedical, or human-machine interface systems. But a big problem in this kind of sensor developments is the combination at one side, the gauge factor, and the other side, the strain. So the stretch possibility of these kind of sensors. So what we investigated in research, okay, I put some extra text, but what we investigate, and I presented the abstract of that paper we published around 3 years ago, we found out a special type of blends on, yeah, people would say that's high-tech research, but finally it's indeed high-tech research, but it's a kind of low-level processing possibility. So we combined, in this case, standard TPU with OBC. By blending them in the right blending percentage, we also involved the so-called carbon black fillers, and by blending them in the most ideal situation you see here on the bottom, we created a kind of sensitive network. And then in this sensitive network, depending on the stretching behavior, we could achieve inside the so-called gauge factor and strain behavior, we could achieve the red dots you see on the slide. We could initiate, or we could develop sensors with high sensitivity combined with gauge factor and strain possibility. So this is research we will further study. And I know, Professor Guillemino, you also like fillers. So this could be perhaps a future possible cooperation. We never know, together with Ghent University and Mackenzie University. Okay, so yeah, I didn't mention in the previous slide, but we investigate TPU, OBC, OBS as matrix materials with fillers, but these ones could be also bio-based materials in the scope of sustainable use of polymers. So in the case 4, taking in mind a little bit the time, in the case number 9, I will explain you somewhat research we are doing more in detail on material science for extrusion-based additive manufacturing. So additive manufacturing processes are mainly divided in 7 groups. So the one I will highlight is the so-called extrusion-based technology, which I discussed also before in the dice well and in the flow behavior of the materials. So what we investigate also in our research group, it's a combination of, at one side, the standard filament extrusion, but also we developed a patented pellet extrusion micro extruder. And then it's very important that you take in mind, we have the pellet feeding system here, but in the first phase, the material is not molten. So, and in our design, we investigate the melting behavior depending on time and speed of the polymer, trying to find out the blending of the material, but also finding out if finally the pressurization is optimal and also temperature for afterwards deposition is optimal. In our investigation we did, in our patent, we have the possibility to control at one side the shear, so the heat, and the other side also the pressure distribution. So it's also recently published in a journal. So we also tried to combine that with the so-called syringe 3D printing, where you have a liquid inside a vessel and with a kind of hydraulic or pneumatic piston system, you push the material out finally of your material or of your nozzle. So we investigate in that case the different kinds of rheology of, at one side, the pellets. You can see them here on the left side. So we analyzed the flow behavior of a pellet. We analyzed the flow behavior of a filament for different mixtures, and then to find out what's the best opportunity. One thing we also combine in this stage is that we also try to find out the aging. What does I mean for that? So when you process a pellet or a filament, when you use a pellet immediately, as mentioned before in this slide, when you use a pellet, we have one-time heat transfer in the polymer. But when we need to use a filament, we first have to produce the filament, and then we use the heat in the nozzle to deposit the material. So this means what we investigate in that one is what's the flow behavior of a pellet, what's the second heating of the material in the filament, and then afterwards, after deposition. So this rheology is investigated, and normally you can see also moving, in this case, our pellet printer deposing the material on the build platform. So that briefly as a small video. So then finally afterwards, we investigate by some imaging, we investigate the morphology structure of different kind of materials, taking in mind, and you see here also, it's in this case PLA material, where we use a percentage of the D isomers due to a patent, we can't mention the composition, which the percent of D isomer in the PLA can be either low or high, and the average molecular mass is low or high, and then we combine that with a plasticizer A and B. So by playing around with our parameters and blending and the different kind of melting points, we investigate combined with the melt flow index or viscosity, the printing behavior, and finally the density and inter and intralayer adhesion of materials. So that's, as example, a part we investigate. So how we mainly do that? Well, we want to develop new materials, could be either be bio-based or thermoplastic. We develop them by blending, but we want to understand also the relation polymer processing and the final material behavior, so the rheology and aging. And then we try to improve also the AM, the additive manufacturing processing. So by optimizing rheology, solidification, and shrinkage in the printing process itself by deposition methodology. So very briefly, you have, for instance, our blend in this case could be PLA for a bio-based material, sustainable material, PLA, PHB, PBS, PBAT. We can blend with carbon black, cellulose, starch, whatever. So we select the material. We prepare the material either in filament or we use immediately pellets, and then we do several investigations on the final part or the blended material to improve, let's say, the amount of materials available for additive manufacturing. So one of the topics we found out is that it's very important in this kind of blending. And so that's a rectangle you can see here in between the table. Almost all of them are around between 8 and 10 of melt flow index. So we investigate that also due to the printing, that when you print with a melt flow index reference point based on the pressure and temperature, which you have to correlate afterwards to your viscosity, when you work in between 8 and 10, then you have good printing behavior. So that we further investigated. We also investigate annealing. Annealing for PLA, for instance, you have the cold crystallization, but after annealing, we avoid this in a stress, this cold crystallization, but also we improve the annealing of the material or the recrystallization of the material, so that finally, as you can see in these two graphs, by annealing the unannealed black material of standard PLA, when we anneal, finally the Vickett softening temperature increase a lot. When we have blends, it does not increase, but depending on the impact behavior, the annealing also has an effect depending on the type of blend of PLA or PLA PBAT. So this is a kind of investigation we also do to see if you need post-processing after your polymer processing or 3D printing. So briefly some image to highlight how we then investigate the brittleness or the composition or the interlayer adhesion of the different materials. So I mentioned already the melt flow, the green region, it's acceptable, even it's above 20, but most optimal, it's melt flow index as an indication point for fast identification instead of viscosity measurements. So melt flow of 10, it's a somewhat ideal processing environment. Talking about fillers, we did investigation together with our colleagues from Ghent University in Austria. And what we investigate with them is combining, let's say, at one side, the processing temperature. Yeah, sorry, this one is somewhat written, I didn't notice myself, it's somewhat written in German. So we have the tensile strength combined with the layer thickness. So you see there is a high tensile strength when we have a very thin layer thickness of the 3D printing. But when we improve the layer thickness, the tensile strength will reduce a lot, taking into account our processing temperature. So what we investigate in this case is the effect of the processing temperature of the 3D printing combined with the layer thickness to see how we can improve that. So, and that's what you see here. That's in the scope of very low temperatures and high layer thickness. Then it looks like this. But when we go up to small layer thickness and high temperature, we have almost no voids and we have a better morphology structure of the material. It's the journal I mentioned here, Applied Polymer Science. It's not involved in this paper, but we have another paper together with Martin Spurk, in which one we integrated carbon fibers. And one of the positive things to integrate carbon fibers or carbon black is the heat transfer, because then you don't have to go, for instance, to 250 degrees. You can process at 200, 210 degrees with carbon fiber filling for a very good heat transfer due to the absorption energy or the absorption ability of your carbon fiber or carbon black fillers inside the blend. So you improve processing in combination, in that case, with the mechanical behavior. Okay, yes. The last case study, very briefly to highlight what we try to investigate in our labs, it's the so-called thermal conductivity of composites. So in general, we know plastic is a very bad heat transfer. Let's say 0.2 compared with steel, where we have 7, 8, or 10. So it's a factor something like 20 difference in heat transfer or heat conductivity. So can we optimize this? Well, where is the problem? Briefly explained. When we have a matrix material with fillers, as you can see here, the most ideal would be a blend like that, because then we have a through plane and an in-plane thermal conductivity, which would be better and which will improve the conductivity, thermal conductivity of a polymer. When this would be, let's say, short carbon fiber or carbon nanotube fillers. But what happens when we do extrusion processing to make plates? Well, the big problem is the fibers will reorient in the flow direction. So we investigate that also on morphology level by extrusion and injection. So we have the fibers oriented like that, then we know we have a very good heat transfer in the horizontal, but in the through plane, it's not good. Can we optimize this? Oh, yes. Do what we call a multiple blend of fillers. So an example we somewhat highlight in this case, you can work, let's say, with one type of filler. This could be, for instance, graphite flakes combined with some carbon nanotubes, or it can be, like you see on the bottom, we combine that with the so-called spherical fillers. This can be either glass fillers, this can be air bubbles. We also tried that by foaming the whole system. So when you reorient, and going back to the previous slide, when you are able inside your processing to reorient them randomly, like we did in our research, you create a kind of interconnective network so that the heat transfer inside or in between your filler system is a lot better. To have an idea what we achieved up to now with these combinations, due to some confidentiality, I can't show the blends we use and the type of matrix material. But for instance, a normal blend of 0.2 could improve in that manner for thermal behavior from 0.2 up to 1.5. So this is an increase with almost, briefly said, something like 6-7%. 6-7 times, so which is very high for thermal behavior, heat transfer, thermal conductivity of polymer materials. So I guess this is also type of research, as I know, which is also interesting, I guess, for Mackenzie University. Okay, so I try to make, let's say, a brief overview in something like 10 cases about what we investigate. So, and no problem, I'm open, try to answer, let's say, some questions and to interact about possible ideas. Thanks a lot for listening.
So thank you so much, Ludwig. So many things we have to discuss here, but I don't know if we have time for everything, but let's open for the questions. First of all, we have a question from Gabriel Pinto. He said, what would be a practical application of the polymeric mode from case study 2? He is concerned with the industrial situation due to the wear of the mode, as you mentioned before.
Yeah, I will try to go to somewhat to the case study to make it somewhat more easy. Okay, yeah, because I lost a little bit my connection to hear the complete question.
Let me say again, what would be a practical application of the polymeric mode from case study 2?
Yes.
He's concerned with the industrial situation due to the wear of the mode.
Yeah, well, indeed, but it's a very nice question. Why I say this, it's so today, this afternoon, this afternoon for Belgium, for you, I thought in the early morning, I had a meeting with a company which cooperates with us in the case of the so-called hybrid molds. Let's say the biggest discussion for the moment together with industry is in which cases can we apply this kind of, let's say, plastic molds. We noticed ourselves that up to now, it can be used, let's say, in the scope of what we call prototyping. So briefly to explain that, normally what we produce, or when you need prototypes, what you produce, you go to 3D printing, you print your material, but it's not the real final quality you want to achieve, let's say polyprop, ABS, whatever. So the big advantage of this kind of hybrid molds is you can produce these kind of molds. Let's say you design the insert, you produce them during night. The day after you need, some post-processing, and in something like 2-3 days, you have your mold. So it's very fast. You have to take in mind the difference, for instance, in crystallinity of a semi-crystalline material, depending on the speed of the cooling. Indeed, by the vapor fusion polishing principle we use together with that company, we have a rather smooth surface, but polypropylene is easy. It's possible to inject polypropylene in the PA material. Also possible is, for instance, ABS material, polyethylene, and so on. Polyamide, we also injected inside polyamide, taking in mind some surface treatments. But that's a question we also got in the same manner today with the company. Can we inject, for instance, glass fiber, reinforced polymers, polyamide with, let's say, 10 or 20% glass fiber? So this is indeed an investigation we did not fully do with this kind of materials. Do we expect wear? Yes, we expect wearing of the mold. Can you avoid it? No. There are some possible techniques we discussed with the company. Probably we can try to put a kind of flexible coating on top of the flexible mold. One thing you never may do that we noticed from the research, when you put a coating, a hard coating on the soft polypropylene, on the soft polyamide insert, after 1 or 2 injections, it cracks like the eggshell effect. So that's something you can't do. But when you have a coating with a kind of lubrication, you can try to avoid somewhat faster wearing, but you will have wearing. But when you then can produce, instead of 3D printing, you can produce in this kind of molds the real polypropylene, polyamide, ABS, what you want, then you have a real final material by injection molding. Perhaps not the optimal parameters, but it's possible to do that. But I agree that wearing of the molds, we investigated, it happens, but not too fast. So you can do 10, 20 parts in standard non-filled materials. Going with filled materials, yeah, it will be perhaps less. But we even did with this mold you see here on the screen, with this mold, as I remember, we did something like 300 injection molds with not so much wearing. But one important thing, pay attention. You need simulation in advance to find out the lowest as possible injection and holding pressure. That's very important.
Let me ask something about this. So have you ever tried to use, even in simulation, some composites with a very higher thermal conductivity, just to check how is the crystallinity on the first layer, and how much time you need to solidify the polymer inside the mold?
Yeah, so you mean if we make the mold insert based on a composite material, you mean?
Yeah, I mean, the last one that you showed me, that you have a very nice thermal conductivity.
Yeah, indeed. Well, we did not yet do that. But what we do for all type of inserts, we first experimentally analyze the thermal conductivity, the heat capacity and density, which we need in the flow simulation. So theoretically, what you say, it could be possible. It's what I did years ago in my PhD research, where we blended epoxy resins together with some flakes of aluminum to make the mold stronger and to have a, let's say, 10 times more better heat transfer. It's a possibility, but the printing system, I didn't in detail mention it here. The printing system we use in this case is a so-called it's a multi-jet fusion, the HP 3D printing. In that one, it's not yet possible to, let's say, combine with fibers to have a higher conductivity of the inserts. It could be a good idea, but we didn't yet do.
So let's move on for the next question. Professor Hélio Ribeiro asks you how to guarantee the interconnectivity between nanoparticles in the dispersion at the same time. I mean, that I think is the last study for the polymer composite with higher thermal conductivity.
Let's say to answer the question somewhat in a broad manner. It's indeed a tricky thing. When you have, let's say, and that's what we try also to investigate, to optimize, when you, for instance, in the scope of the thermal conductivity or in the scope of the sensors, in that case, you have the matrix material and you have your fillers, which can be, let's say, flakes, carbon nanotubes, carbon black, whatever. The interconnectivity, when I understand well the question, the interconnectivity is indeed a big question. When you want to optimize the thermal behavior, the thermal conductivity, normally the materials are not really in contact with each other. So you need to find out, and that's something we have in mind also, we try to do that. What you need to do is to, let's say, that's more, it's not my research field, it's a field of my colleague Dagmar Dogo, for instance, in the chemical polymer chemistry, when you would be able to create a backbone inside your polymer structure, which you can control. And that's one of the ideas we have together with reactive extrusion. When you can initiate inside your reactive extrusion a kind of reactive backbone system, which then during the solidification has an effect on the reorientation of a polymer structure, and in the same manner a reorientation or an interlink of your filler system, this could improve at one side, let's say, thermal conductivity. We know it's a holy grail, let's say, when we would succeed. Another one related to the sensors. In the sensors, it's comparable too. You must try to mimic or to guarantee a uniformity of the filler dispersion. This is really not easy. It takes us a lot of time in that research. When you can mimic or when you can optimize in the processing the dispersion of your fillers in a uniform manner, then you also can guarantee an optimal sensor based on the stretching. When you stretch your sensor, the distance in between the fillers will increase or decrease, which is, let's say, also the effect of the sensor effect, the resistivity in your sensor. So it's not easy. You need to optimize the blending process. You need to optimize the combination of the dyes. Well, and the flow behavior. So yeah, it's not easy, honestly said.
Because it is, if you think about percolation for thermoconductivity and electrical conductivity is quite different.
Yeah.
Because
Yes.
for thermo you have a low amount of filler because you don't need to have this contact between the fillers.
Yeah, indeed. You for the resistivity for sensors, you do not want to have the contact, but you want to control the dispersion, the position, to have a good sensitivity of your growth factor and so on. And it's not easy. That's why also we have the combination of the TPU and the OBC, for instance, to create. We did it for TPU combined with carbon black. But we noticed, okay, it's not optimal due to clogging of the material inside, not uniform dispersion. And by using what we call a dual blend, first blending, I have to think about, we first blend the TPU combined with the carbon black. Then we afterwards did a B-blend or tri-blend with the OBC. We could achieve a good general blend to achieve a good percolation effect. And it's indeed not easy. Yeah.
So let's move for the last question. Gabriel again. Gabriel is my PhD student.
Okay.
Okay, he said, really nice work, congratulations regarding the thermoconductivity of composites. What's your opinion about using more than one 2D materials instead of a combination of different geometries?
Wait, when I will understand, so using 2D materials instead
of like graphene and boron nitride in the two-dimensional aspect ratio.
Yeah, well, because it's a little bit confidential, I can't say all details. It's in cooperation with a company. We are further developing what we experienced. Mm-hmm. A small info on that. What we noticed. You can work with a very nice combination of, let's say, spherical fillers and 2D fillers when you select the right composition or the right amount of blending of your fillers. I didn't show the table because it's confidential. But when you blend, for instance, what we did, polypropylene, polyamide, copolyesters as matrix material to improve their thermal conductivity, we blended them with a mixture, a 3-blend filler of, let's say, at one side, a very small amount of carbon nanotubes, at the other side, flakes, and on the other side, also spherical fillers. By blending them and having a good dispersion mixing of them, we improved from 0.2 to, I thought, up to now 1.3 thermal conductivity. So that's, let's say, easy said, the tricky thing about that. We, for the moment, we want to publish that research. So we are in discussion with the company, talking about not the, let's say, the real content of the materials, but talking about, let's say, flake 1, spherical 1, CNT 1.
This is the next question of the Gabriel. How about the content of this?
Yeah, but it's indeed, we combine, let's say, borate nitride, CNTs, graphites. These ones we combine in the optimal mixture, but taking in mind that we then try to investigate also the production of these kind of fillers. Some of them we select in spherical, other ones we select them in flakes, and other one, let's say, like carbon nanotubes in 2-dimensional, depending on what we need.
I thought that a lot of change you have in the rheological behavior of this polymeric matrix or blends. So you have to think about the processing, the molding with the amount of different kind of fillers.
Yeah, indeed. You have to, so what I didn't tell all details on that one. So that's the one we will normally plan to publish. We did, let's say, with filler ABC, we did different type of blends. All of them always, I thought, oriented to something like up to 20% of fillers, but taking in mind the rheological aspects, the flow behavior, the possible dye swell. So all these things you have to analyze in advance. Yeah, I don't know if you know the Thermo Fisher or Thermoscientific Hake, small conical micro extruders. So we use these kind of devices to test small batches rheologically, and then afterwards we go to, let's say, somewhat larger scale from 1 to kilo, and then to a semi-industrial scale. So if we start micro, milli, and yeah, different levels. But indeed, the rheological behavior and the processability must be investigated in advance with different mixtures before you go to a real extruder itself.
So I think we reached to the end of our seminar. Professor Ludwig, thank you so much to have you here in this very interesting and nice presentation, and you can also see your projects and then what you can do together. I know you have a few questions to discuss after that seminar, yeah. But let's talk later in another day. So, yeah. Because they student, I think I don't know if I'm sure it's more 1 hour they have class here in Brazil, the night class. So let them free.
Yeah, but
it's their night.
Yeah, it was a great pleasure for me to let's say present some insight in research we are doing. Yeah, we can't talk hours, let's say, but it's no problem afterwards. So I can send later on by email PDF of the presentation to you. You can spread around to your researchers and students. And when they would have questions afterwards, it's no problem. They always can contact me. I will try to respond as fast as I can to their questions.
Thank you so much.
No problem.
Thank you.
Okay. So I would say, yeah, for you and for the researchers, enjoy it's already evening for you now, almost evening, I guess.
Almost evening, yes.
Yes. So for us, I have to check it. It's 10:30 for us here in Belgium.
It's quite late. Yeah.
Yes,
Don't worry.
So thank you very much, Ludwig. Thank you, Guillermino, for chairing this session, and it was very nice presentation. I'm sure the students enjoyed it a lot. I just want to say as a last thing that we have the next seminar in 2 weeks. Right, on the 21st of October, and it's going to be given by Professor Mauricio Terrones from Penn State University. Okay, so stay tuned. We'll publicize all the information later on. Thank you, everyone, for staying and for listening, and thank you, Ludwig, for the nice presentation. Bye-bye.
Bye, guys.
It's a pleasure. See you next time.
See you.
Bye. Yeah.